Okay, so we are going to be starting section 6.2 today. So this section has a couple of tricky parts to it. We're going to start out with this equation that they give us. And the idea of what we're kind of doing here for this section is you all will be given for the first, there's kind of three different parts of this section. The first part is we'll be given kind of a graph of maybe, let's say, like a parabola. So let's say we have a parabola and we're kind of looking at it from above. So let's say this is the x-axis and this is the y-axis. And our parabola, maybe it opens downwards like this. And what we'll be doing is maybe we have cross sections on this parabola that are squares. So the base of the cross section is the width of the parabola, and therefore the height of the square is like that.
Pardon the interruption.
So if we
Today's
get
lucky duck winner is duck number 91. Duck number 91. Come on down to 203 and collect your prize.
So basically, as the width of the parabola between the width here gets bigger, the squares get larger. As the width gets smaller, that generates smaller squares. And so we'll be dealing with, there's kind of like some sort of boundary. You'll be making some sort of geometric shape, like maybe squares or semicircles. And we'll be calculating the volume of having a bunch of these squares, say for example, stacked on top of each other. So what this is the equation we're gonna be dealing with is, we're gonna say this will be the volume of, we'll say as the integral of the cross-sectional area. So what this is gonna do is we're gonna let A of y be the area of the horizontal cross-section at height y. Be the area, of the horizontal cross-section. We'll say at height y. Of a solid body extending from y equals a up to y equals b. Then we get the following thing happen. Then the volume of the solid body is going to equal the integral from a to b of the area with respect to y. So basically, what this means is, like in this problem here, the area function would be represented by one of these little squares that would be represented by the a of y. That would be each of these squares is a cross-sectional area, and we would be integrating them from the top of the parabola down to whatever barrier you set down there. So we'll do a couple examples, try to hopefully get this where it makes sense and seems good. So first example, we want to calculate the volume we'll call it V, of a pyramid of height 12 meters, whose base is a square of side 4 meters. I think for these, it's helpful to draw a couple different views of your object so that you can kind of visualize what's going on here. So we'll say, okay, here's our y-axis, here's our x-axis, and basically what we have is a, sorry, let's draw it a little carefully. We'll say here's our pyramid. It's going to have a base that is 4 by 4. Looks like this. Oh man, guess that's good enough. So we have our kind of pyramid with a base that's 4 meters and 4 meters on a side. The overall height of this pyramid from bottom to top is 12 meters. And what we're going to need to do is we're going to say if we are at a height, so if we're at some height on this pyramid, we can see our cross-sectional area will be a square. So I'm going to draw that square out to here. And this square, we don't know really the length of the side of this square. So we're going to call this square here, we're going to call S will be the length of a side. So my square will be S by S. And the height of the square, we don't necessarily know how tall that square is. So we're going to say that the height of this square is Y. And if the height of the square, if the square is at height Y, then the top part here from the square up to the top of the triangle, that will be at 12 minus y. So what we're going to do next is we're going to use kind of the side view of this thing here to, well, basically we're going to try to generate our area function. So let's do that first. We know the area of these squares, a of y, that's going to equal s squared, because it's s and s is the side. We need this in terms of y, not x. So we need this in terms of y, not s. So I need to know what is s in terms of y. So this is where I'm going to use the side view and some similar triangle stuff. So basically, if we look at our pyramid, the base here is 4. It goes up 12 meters. This is the side view of our pyramid. And we'll say it goes up to a height of 12. We said this little bar here, this S by S, that would be at a height here, which we said is just a random height y, which means that its length of its side is S. And from here up to here is 12 minus S. So I'm going to kind of form two right triangles out of this. We're going to say if we put a dotted line down the center here, the whole length of this thing from side to side is 4, which means from here to here would be half of 4 would be 2. So I have a triangle that's, this triangle here that's base 2, height 12, and I have a similar triangle whose base from here to here is 1/2 s, and whose height is, half of s, and whose height, I wrote 12 minus s, that's a mistake. It should be 12 minus y over here, so whose height is 12 minus y. So from similar triangles, we can say the base of the big triangle, which is 2, over the height of the big triangle, which is 12. And again, the big triangle I'm kind of dealing with, let me choose a different color so you can see real quick. This right here is the triangle I'm currently talking about with base 2 and height 12. So that one I just outlined in red, that's base 2, height 12. That's similar to the second triangle, which will be the smaller triangle here, which is base 1/2 s and height 12 minus y. So that's going to equal the smaller similar triangle, whose base is 1/2 s, and whose height is 12 minus y. Now what we're going to do is we're going to try to solve this equation for s. And once we know what that equation is solved for s, we can then go over here to this s squared, and we can plug in. So 2 over 12 is is 1/6. That equals this 12 minus y. I'm going to actually multiply it across first. So we'll say times 12 minus y, and that will equal the 1/2 s that's still up there. I'm going to go through and multiply everybody by 2 here. And so we'll multiply this by 2. We'll multiply this by 2. So these will cancel. 2 times 1/6. 2 times 1/6 is 1/3. 2 times 1/6 is 1/3. So we get 1/3 times 12 minus y is our s. So this is our s, what s is in terms of y. So I'm going to go over here and plug that in. So that says that my area function will be, open parentheses, 1/3 times 12 minus y squared. 12 minus y, whole thing squared. So instead of s squared, if s is 1/3 times 12 minus y, I get 1/3 times 12 minus y, whole bit squared. 1/3 squared is 1/9. And the 12 minus y squared, trying to think. I guess we could just write it as 12 minus y squared like that. We have this basically is our cross-sectional area right now. So we found our cross-sectional area. So this cross-sectional area. So this is what we're going to be integrating with respect to y. So this is the volume of the solid body will be the integral from a to b of the cross-sectional area dy. So we're ready to set up that integral now. We're going to integrate from the bottom of the triangle, which is 0, up to the top of the triangle, which is 12. So our integral is going to run from 0 up to 12. This will tell me the volume of the solid body. It's going to be the area function, which is 1/9 times 12 minus y squared dy. Now, I can either FOIL this out and solve it that way, or I could use u substitution. I think I'll go u substitution here. I'm going to push the 1/9 out front. So I get 1/9 integral from 0 to 12 of 12 minus y squared dy. We're going to let u equal the inside part, 12 minus y. So it's the part inside the square, which is 12 minus y. Then the du part, derivative of 12 is nothing. The derivative of negative y is -1. So this will be just negative dy. So I have a positive dy here. So to get a negative dy, if I put a negative in there, I would put a negative out front to keep stuff balanced. And now I can go to my new integral in terms of u. I'm going to get new limits of integration. And I will get, basically I'll get 12 minus y is u. So I'll have u squared, and negative dy is du. So I'll have my integral looking like that. When I get my my new limits, if I put 0 in, 12 minus 0 is still 12. And if I put 12 in, 12 minus 12 I guess becomes 0. So we say, okay, this is going to be -1/9. The integral of u squared will go to 1/3 u cubed. And my limits of integration will be 12 down here to 0 up here. So basically what I have is -1/27 of u cubed from 0 down to 12. So I'll plug those in and see what happens. When I put 0 in, I get -1/27 times 0 cubed. Then I get minus -1/27 times 12 cubed. 0 cubed times -1/27, that's just 0. Minus a negative becomes positive, which is good because this says we're going to end up with we're going to end up eventually with a positive volume, which is what we want. Let's see here. Whoops, my 27, I have 27 there. I accidentally changed it to a 12 there. Let me fix that before we get much further. So that's a 27 still. 12 squared is 144. If I multiply 144 by another 12, let's see, that's 8, 8, 2, 0, 4, 4, 1, 8, 2, carry the 1. That's 7. So it looks like we get 1728 over 27 for my volume, which 1728 over 27, that ends up being 64. So my volume in this situation, that is 64. And we would have, let's see here, did they give us measurements on this? Yeah, everything's meters. So this would be, the volume of our solid body would be 64 cubic meters based on that. So these problems have a little bit of setup. First, you kind of want to draw a picture to see what's going on. Generate your cross-sectional area. You need the cross-sectional area. In this case, since we're integrating along the y-axis, we needed it in terms of y. We had to use similar triangles to get it in terms of y. Then we got our cross-sectional area in terms of y. Then we were ready to put that in and integrate it from 0 to 12 of dy, and the rest of this was just calculating that integral. So we'll look at the second one and the third one, and then we'll stop on this initial part here. So for example 2, we say compute the volume of the solid in figure 4. Okay, compute the volume, I'll try to draw it down here, of the solid below. And then they'll have some extra stuff. So the solid that they give us, they have it kind of drawn like this. Here's our x-axis. Here's our y-axis. It is a parabola along the y-axis, like that. And the cross-sectional area of this parabola are half circles. So it's a parabola where you get larger and larger semicircles, and we go till we hit the x-axis, basically. So it's basically this three-dimensional object, some sort of looks kind of like maybe a bullet that's been cut in half or something. So the cross-sectional area are semicircles. They give us some extra information about this. They say the base of this expression, the base is the region between the inverted parabola and they give us an equation, which is kind of nice. Y equals 4 minus x squared, and the x-axis. Okay. The vertical cross-sections perpendicular to the y-axis are semicircles. So the vertical cross-sections perpendicular to the x-axis are semicircles. Okay, so a couple things. First of all, if this is y equals 4 minus x squared, that's an x-axis reflection. It shifted up 4, which tells me that 4 is where the point, y equals 4 is where the point there hits. The x-axis is 0, so my integral is going to run from 0 up to 4. What we need to do is we need to figure out, so our goal here initially is to figure out what is the radius. We're going to need the radius of the semicircle in terms of y. Because we know the area of a semicircle, so if we say area of a semicircle which we'll call a of y, that will equal pi times r squared divided by 2. So we need to figure out what is the radius in terms of y rather than in terms of r, because our integral is going to run along the y's. So I'm going to rearrange this expression here. If we have y equals 4 minus x squared, we can, let's see, what can we do? We can move the x squared over, and we can pull the y back over. This will become x squared equals 4 minus y. To get rid of the square, we'll say x is plus minus the square root of 4 minus y. And so what we get is basically this arc of the parabola from here down to here. That arc of the parabola, that equation will be the square root of 4 minus y. And the arc on the other side of the parabola, so the one that goes from here on up, that one there will be the negative square root of 4 minus y. So basically, if I'm looking at my parabola, if I'm trying to figure out the radius of a semicircle in terms of y, if you're at a height here and you go over here, the distance, since this right here is x, this distance will be given by this equation here. So basically what we're saying is this right here, that is the radius that tells me the distance from the y-axis on over to the parabola. And since the parabola is symmetric, that will be the radius that we're going to then use and generate a semicircle from. So this will give us pi times square root of 4 minus y whole thing squared. So we're using this for our r, divided by 2. This will be, we'll write it as pi over 2. When you square a square root, that cancels out, so we'll get it's pi over 2 times 4 minus y. That is our area equation. And I'll distribute the pi over 2 and do a little bit of math with it. So we'll get it'll be 4 pi over 2. 4 pi over 2 reduces down to 2 pi. And then we'd have minus pi over 2 y. So this right here, this is our area function that we were kind of looking at. This is what we're going to set up our integral. Our integral is going to start here at x equals 0. It's going to go up and stop at x equals 4. All the semicircles, as the y value changes, this right here will give us the area of each of the semicircles each step of the way. So when the y is down here, you'll get bigger semicircles. When the y is way up here, you'll get smaller and smaller and smaller semicircles. So this equation here tells me the this bit here tells me the radius, and we use that to generate the cross-sectional area. So we'll integrate this from 0 up to 4 of 2 pi minus pi over 2y dy. And this right here is set up to integrate. We would get 2 pi y minus, let's see here, y is going to go to 1/2 y squared. There's a pi over 2 in front of it, so it would be minus pi over 4, because pi over 2 times 1/2 is pi over 4 y squared. Whole thing evaluated from 0 up to 4. So we will substitute on in for this. We will get 2 pi times 4. We're using fundamental theorem of calculus part 1. Minus pi over 4 times 4 squared. And that will be minus 2 pi times 0 minus pi over 4 times 0 squared. Well, 2 pi times 0 is 0. 0 squared is 0. Pi over 4 times 0 is 0. 0 minus 0 is 0. So this entire term over here is just 0. So all the work's going to be what's going on this side. 2 pi times 4 is 8 pi. 4 squared is 16. 16 divided by 4 is 4. So this is 8 pi minus 4 pi. And 8 pi minus 4 pi, that will equal 4 pi. Let's see, do we have units on this? Is this centimeters or meters? They don't specify units, so we say, okay, this is 4 pi, and the units on this, we would just say it's units cubed if they asked us for what the units are. It didn't specify that that was meters or anything. Okay, so that is second one of these. We have the base. They tell us what the cross-sectional areas are, and we have to figure out the, in this case it was a semicircle, so we needed to know the radius in terms of y. We used this equation right here, and we solved it for x because the radius r would be the distance x there, and then we were able to plug it into the equation for the semicircle and generate our area equation, and then we integrated the area equation over the appropriate limit. Okay, so third example. And then this is that'll wrap up this first couple problems here. So we'll wrap it up and say that's part 1. And we'll do the rest of it in a bit. So they want us to compute the volume of a sphere of radius, and they call it radius capital R. The book does this integration. If you look along in the book does this along the x-axis. So I'll set it up and do it the book's way. The previous two we did integration along the y's, but we'll show you what it looks like when you integrate along the x's. So we have a sphere of radius r, so we'll pretend that that's a good circle. It's radius r. And the cross-sectional areas on this, so if it's radius r, I guess that means it starts here at r, and it will go over here to negative r. And the cross-sectional areas of this thing will be circles. Let me try to draw this a little better. That looks horrible. Let me use the little circle tool. So the cross-sectional areas of this shape here, these will be circles, so we can see the circles will get bigger as you approach the middle, and then as you approach the edges here, the circles shrink back down. So what we need to do is to get the area of the circle, we're going to need to know the radius of the circle. So we need to know basically if you were at kind of a random point on the circle, we need to know when you're at a random point on the circle, what is your x, or I guess what is the height of that right there, which would become the radius. So we say if we call this right here little r, since we know the circle is radius capital R, if I drew a line from the center out to the top here, let me use the line tool again, that would make this look slightly better. If I drew a line from the center out to that point there, since the sphere's radius r, that would be radius capital R. So we have little r here, we have capital R there. The distance this is over, this would be x units over. We're going to try to use this triangle here, so let's try to draw that triangle. We say, okay, you would be at a x value of x, your height would be little r, and the hypotenuse of this would be capital R. So basically, we've generated a right triangle that's little r, x, and capital R. And little r here, this right here, this will be the radius of the circle cross-section. So if we use Pythagorean theorem, we can say x squared plus little r squared equals capital R squared. which would say little r squared equals capital R squared minus x squared, if we just scoot the x squared term over. To get rid of the square on the little r, we take plus minus square root, but since this is a distance, I want to keep the positive square root. So we'll say little r is positive square root of r cubed minus x, sorry, should be r squared minus x squared. Okay, so our little r here, this is capital square root of capital R squared minus x squared. So this is the radius of the cross-sectional area, which means when we go to set up the rest of this problem, the cross-sectional area itself, a of x this time because we're integrating from left to right along the x-axis. Cross-sectional area itself will be pi times the radius, well, it's pi times little r squared. And we just said, well, little r squared is the square root of capital R squared minus x. So it's pi times the square root of r squared minus x squared squared. Square gets rid of the square root, so we get this is pi times r squared minus x squared for our cross-sectional area. And so now we have our equation for our cross-sectional area. When we integrate this, we integrate it from negative r all the way. We're going to integrate from negative r all the way up to capital R over here. So our limits of integration are going to be be negative capital R up to positive capital R. So we go and set up our integral. We'll say negative capital R up to positive capital R. We're going to integrate the area function, which is pi times r squared minus x squared dx. I'm going to push pi out front of our integral since it's a constant. In this expression, x is the variable, so we go to integrate this. We get pi times the integral of r squared. R squared is a constant. We're integrating it with respect to x, so we just put an x after the r squared. You treat the r squared like it was 7. If I integrated just 7, I would get 7x. Here we have r squared, so I integrate it with respect to x. I get r squared x. Minus the integral of x squared would be 1/3 x cubed. And we would be evaluating this from negative r up to positive capital R. So I'll plug that on in. I will get pi times r squared times a capital R minus 1/3 r cubed minus pi times, it's r squared times a negative r minus 1/3 times negative r cubed. So this is from Fundamental Theorem of Calculus Part 1. You substitute positive r in for the x's, subtract from it the lower limit substituted in for the x's. So let's see, what does this become? This becomes pi times, let's see here, that's r cubed minus 1/3 r cubed. Okay, and then this is minus pi times, let's see here, that's negative r cubed minus negatives plus 1/3 r cubed. So if we think about this, r cubed we could say is 3/3 r cubed. Take away 1/3 r cubed would be 2/3 r cubed times a pi. So this would be pi, we could say 2 pi over 3. It's 2/3 pi r cubed. We have, let's see here, this is negative 3 over 3 r cubes plus 1/3, that's negative 2/3 r cubed minus pi times negative 2/3 r cubed minus the negative is positive. So this will be positive 2 pi over 3 r cubed. 2 pi over 3 r cubed plus another 2 pi over 3 r cubed will be a total of 4 pi over 3 r cubed. And that will be the volume of our sphere. That'll be our equation. And if you all remember, this right here is equivalent to, if you remember, there's a volume equation for a sphere that is 4/3 pi r cubed. This right here is, these two things are the same. So this gives us the correct equation that we would expect to get back if we were asked to calculate the volume of a sphere. Okay, so we'll stop on there, say that that's part 1.